introduce Daniela?
Go ahead.
Thank you. All right. So, hello everybody. I'd like to welcome you to an op-ed talk as part of the Summer Institute program in 2020. I'm Bruce Weir from the Department of Biostatistics at the University of Washington, and it's my pleasure to introduce this afternoon my colleague Daniela Witten, who's a professor of statistics and biostatistics at the University of Washington. She's also the Dorothy Guilford Endowed Chair in Mathematical Statistics. Daniela's research involves machine learning with applications across many fields, including genomics, neuroscience, and other fields. And she's been thinking about relevant issues recently. So we're looking forward to having your thoughts, Daniela. Over to you.
Great, thanks so much for the intro. So this is such a fun time to be thinking about prediction and modeling, since of course it is in the news so much these days within the context of COVID-19. And so today I'm just going to give you like some of my thoughts about predictive models, and in particular predictive models for COVID-19, why they're important, what their good use cases are, and what we need to be careful about. So first of all, I just want to say this is important. A lot of our main questions that many of us are thinking about really boil down to questions of predictions and projections about the future. So for example, this is from the New York Times. When is it safe for schools to reopen in California? From NBC News, coronavirus, when will schools reopen? And of course, like these headlines are making it sound like schools are just gonna like magically either reopen or not reopen on their own. But of course we know that that's not true, and it should be, hopefully will be, very intricately linked to the science. And so here's a headline that really starts to get at that a little more, which is that if coronavirus transmission levels don't decrease in King County, then school buildings should not reopen in the fall. And so the point is that these predictions or these projections that we can make about coronavirus are tied to public policy and decision making in a very intimate and intricate way, or at least we certainly hope that they are. And now even Trump is saying that schools in coronavirus hotspots perhaps should not be reopening in August or September. So this is really front of mind at this point for everyone, no matter whether or not you have kids in school and no matter which side of the aisle you're on. So here's an article from The Lancet talking about school closure and management practices during coronavirus outbreaks. And it's really a review of what's known in the literature. And so the question that I just want to talk about today is if we're trying to make decisions about the future on the basis of statistical models or mechanistic models, and I'll talk about what I mean by that in a couple minutes, what should go into those models, what would make a model trustworthy, and what does it mean, in my view, for a model to be able to pass the sniff test, because these models have the potential to be so incredibly important as they inform all of our decision making moving into the coming months and even years. So the first thing that I want to say is, if you've been following this area at all, there's a ton of models out there. So this is the California COVID assessment tool displaying some short-term COVID-19 forecasts in California. And all the different curves here are basically showing a bunch of projections from about 15 different models. So like the black dashed line is the present day. On the left of the black dashed line is historical data and projections. So the black dots are the actual numbers of hospitalizations in California. And on the right-hand side, you can see the projections for a bunch of different models. And one thing that we notice is that there seems to be really a broad range of what these models are showing on the right-hand side. So we have like the model in green, which looks like it's a projection from MIT, which shows that, you know, starting right on the other side of the dashed line, hospitalizations are going to jump by 15,000. And then on the other end of that, we have the blue dashed line, which is all the way on the bottom here. And that's a model coming out of IHME, the Institute for Health Metrics Evaluation, which somehow seems to be projecting that overnight hospitalizations in California are going to drop by 5,000. So both of those, to me, seem a bit surprising. And then, of course, most of these projections are sort of more in the middle, showing that the hospitalizations in California are going to continue along the trend shown by the black dots, while also increasing. And so here's a similar set of forecasts coming out of the COVID-19 Forecast Hub. So here we see the total number of deaths in the state of Washington, which is of course where I am, over time on the left up until looks like around mid-July. And then on the right are results for about 5 different models for the next couple of weeks. So projections for the number of incident deaths in the next couple of weeks. But if you use this forecaster, actually, you can get access to many dozens of models. Although if you try to display all of them, it'll be hard to see what you're looking at. And also different forecasts have different targets in terms of whether they're showing deaths or something else, and whether they're showing results for Washington or a different state. Okay, so there's a lot of models out there. And one thing I just want to say is like, it's crazy. I mean, if you are thinking, if statistical modeling is something that you think about, then like, it's really fun to see these types of issues talked about in the news, and often in a very intelligent way. So this is like the headline from the Washington Post, which pandemic model should you trust? Here's how to evaluate them, with some like not bad ideas for how to evaluate models. And actually my favorite part, and I should have circled this on the slide, is the tagline that says, don't rely on just one. So if you know anything about statistical learning, like a really big idea is the idea that ensembles can often do really well. So you can develop, 28 models that all sort of work pretty well individually. But if you average them, you're going to actually get the best possible model. And that really ties into some fundamental ideas like the bias variance trade-off, where by averaging, you can reduce the variance without hurting the bias. So this is what the Washington Post has to say. And then it's also been fun reading some news coverage that actually does a pretty good job of like poking holes in some models that have been unsuccessful. So for example, there's been a very high profile COVID-19 model out of the Institute for Health Metrics and Evaluation here in Seattle. And there's been a lot of coverage from very mainstream media outlets talking about the fact that the projections from this model don't pass the sniff test, and I'll talk more about that in a couple minutes. But for example, here's a headline from Forbes. Even the National Review isn't happy with that model. Here's a headline from early May, enough already with the IHME model. And then Vox, I think, provided maybe the best coverage of this model. This coronavirus model keeps being wrong. Why are we still listening to it? And in particular, this particular model, the IHME model, has gotten a lot of attention because it's had very rosy and optimistic projections of how many deaths the United States would see due to coronavirus. Just a few months ago, it was projecting just 60,000 deaths through the fall. And of course, we passed 60,000 deaths a long time ago. But for me, the really striking part is that like we're at this national moment right now where essentially like statistical modeling is so important that like mainstream newspapers or mainstream news outlets are having just like their regular journalists without even like specific expertise, for example, in statistics, cover these models in a very serious way. And I think if you had asked me like 8 months ago, are we in 2020 going to be in a situation where like statistical models are something that a lot of people are really talking and caring about, and that's like getting a lot of news coverage, I certainly would have said no. But here we are. So I think the real things we should be thinking about when we talk about these projection type models for COVID-19 are these models correct? And also, are they useful? And of course, a model could be correct potentially without being useful if it's modeling the wrong thing or something that's not really of scientific interest. And alternatively, a model could be useful without really being correct, in the sense that a model could provide projections that aren't really accurate. They still tell us about what trends we should be expecting, and also give us hints about what type of interventions might be the most effective, even if the actual projections that are coming out of those models are not so accurate. So these two questions are related, but they're not quite the same. So here's a really nice perspective piece that was just published yesterday, actually, in the New England Journal of Medicine, called Wrong But Useful: What COVID-19 Epidemiologic Models Can and Cannot Tell Us. And I was really impressed by this article because it does a really good job of laying out sort of the different ways we can think about modeling and what the points of these different models might be. But the questions that I'm going to think about today very briefly are, can we project future cases, hospitalizations, and deaths and so on using these types of COVID-19 forecasting models? What is the uncertainty associated with these estimates? And also, how are these projections affected by changes in our behaviors? So first, I'm just going to think about how we can project whatever we're interested in projecting, which could be cases, hospitalizations, or death. It could be on the county level, on the state level, on the national level. But the first thing we need to do if we're thinking about a model is to decide, like, what is it that we're trying to predict? Like, what is the response? What is the sort of the unit for which we're doing that prediction? So again, is it on a very local level or on a much larger scale level? And we also need to think about what data we're going to use in order to make those predictions. So it's actually amazing how much data is available out there. So this is a screenshot taken from this COVID-cast modeling project that's at Carnegie Mellon University. And they have a ton of data through their website that's available to all. For example, doctor's visits, hospital admissions, symptoms that people are reporting through a Facebook survey that is getting shown by Facebook to users. These people at CMU, they also have access to data from a company called SafeGraph, which sort of does mobile tracking. So on the basis of this data from SafeGraph, they know how many people have been away from home for more than 6 hours, how many people have been away from home for 3 to 6 hours. And of course, that gives us some sense of like the amount of social distancing that's going on and whether or not people are staying home. Search trends, and then of course, like more standard epidemiological measures like number of cases per 100,000 people, number of deaths per 100,000 people, and so on. And this data is open to the public, and it's actually available on the county level, I believe. And so this is really just an incredible resource. And this is just a small example of the type of data that's available out there, really publicly available to you if you're interested in playing around with any of these models. So here's a screenshot from the same COVID cast at Carnegie Mellon. And so what you can see, like, for example, here, we're looking for July 18th, 2020, so just 6 days ago. On the county level, the proportion of people who went away from home for 3 to 6 hours using this COVID cast data. And so we can see, you know, some regions of the country are darker red than others, indicating regions where right now it appears that people are maybe not staying at home as often as in other regions. Okay, so the point is there's a lot of data out there. So now once we have the data, we need to think about, of course, what we're trying to model. So we could be trying to model cases or hospitalizations or deaths or something else. But once we've done that, once we've made that choice, we need to think about how we're going to do the model. So I basically think about models as falling into 2 categories. There's statistical models and there are mechanistic models. So when I think about statistical modeling, I'm thinking about something like an autoregressive model. So one really nice thing about a statistical model, like an autoregressive model, is that it can incorporate all sources of data. So like if you give me a new data feed, like the number of people who left home for more than an hour today in a particular county, then I would immediately know how to incorporate that into a statistical model. I would just add a new predictor and just refit my coefficients. But one thing about statistical models that can make them a little bit challenging in this context is that they ignore our scientific understanding. So like based on many years of epidemiology research, we have a pretty good understanding of how virus dynamics work, how infections spread. And if you fit a statistical model like an autoregressive model, you're just completely ignoring that. You're pretending that that viral transmission or that infection or that death occurs completely as a black box process. And you are just in no way trying to take any advantage of what you do know about the underlying process here. And one consequence of that is that you can end up with projections for the future that don't pass the sniff test, like that are scientifically completely implausible as a result of the fact that you are not incorporating your understanding of what's plausible into the modeling process. So I think that statistical modeling, if done well, can be really successful in the context of coronavirus projections, but we do need to be careful. And once we have the model, we need to apply our scientific understanding in order to see whether or not this passes the sniff test. And I really do think about these models in terms of the sniff test. Like if this is a model that you can show the forecasts to a reasonably informed person, and they're like, wait, but like that doesn't make sense because, you know, there's like only 7 billion people in the world. So how can you predict 9 billion people are going to have coronavirus by 2021? Then like that didn't pass the sniff test for me. And that's maybe an extreme example, but you might be surprised if you look into some of these models a little bit more carefully, how easy it is to realize that they just don't pass this sort of common sense sniff test. So the other thing that you can do is take a more mechanistic modeling approach. And some of you may be enrolled in SysMid this summer. So then you've likely seen some of these approaches. But one example is a susceptible, infected, recovered model, or an SEIR, which is susceptible, exposed, infected, recovered model. And the idea here is that instead of just like, slapping a linear model or a non-linear model onto our data and seeing if it sticks, we can instead use our understanding of the underlying epidemiological process in order to really come up with like a model that makes sense scientifically and epidemiologically. So this is appealing in a lot of ways because it uses what we know, but on the other hand, it can't readily incorporate all of the sources of data. So like, it's not clear how you would use the information about how many people have left home today for more than 3 hours into one of these traditional epidemiological models. And furthermore, because one of these models takes sort of a very particular functional form, if the parameters of the model are wrong, then this can go very, very wrong. And the other thing to realize when we're thinking about one of these mechanistic models is that the parameters, even though they seem like some like natural epidemiological constants that we're just trying to estimate, the parameters themselves are a function of the context. So for example, if you've heard a lot about R naught in the context of like how much transmission there is of coronavirus, that's a parameter that's a function of the location and the time. It can change with people's behaviors and so on. So just to be clear, when I'm talking about an autoregressive model, I just mean like, for example, this really basic regression model where we're trying to predict XT, which could be, for example, coronavirus hospitalizations at time t as a function of coronavirus hospitalizations at the previous capital K time points. Or maybe you want to include some other predictors like the number of cases at the previous K time points, the number of people who left the house for more than 3 hours at the previous K time points, and so on. But at the end of the day, what makes this model autoregressive is that it involves previous time points in the prediction for the current time point. And you're going to fit a model like this using, for example, least squares or some other statistical fitting procedure. And by contrast, when I'm talking about a mechanistic model, I mean a model that says, for example, that like some people are in the susceptible compartment, other people are infected, other people have recovered, and that tries to explicitly model the dynamics of transmission between these three states. Okay, so those, in my view, those are like the two big ways we can think about doing this modeling. The next thing to think about is what's the uncertainty associated with these estimates. Gosh, I'm running out of time. So maybe just to wrap up.
Yes, you are running out of time. 2 minutes.
Sorry about that. Well, just what's the uncertainty associated with these estimates? Well, I think about this in terms of a sniff test. So I'll just tell you, this does not pass the sniff test to me. These were projections released by IHME that showed that the number of deaths per day we're going to decrease to 0 with a confidence interval between 0 and 0 in mid-May. Does not pass the sniff test. That didn't turn out to be correct, but it sort of should never have been released because I don't think a lot of people would look at this and think that that is like a plausible prediction. And by contrast, here was the IHME's prediction for total number of deaths at around the same time. We can see the confidence intervals are much wider. And so in this case, whether or not it passes the sniff test, I'm not sure, but at least it doesn't immediately stand out as wrong. So finally, the last thing I want to say is if you're interested in how these projections are going to be affected by changes in our behaviors, so that, for example, we can do the best things we can in order to make it as likely as possible that schools can reopen, at least at some point in the coming academic year, then we're getting into causality questions. And it's really important to think when we're deciding what kind of model to fit, are we going to be better able to answer these causality questions within the context of a mechanistic model or within the context of a statistical model? So that's all that I had to say. Sorry that I ran over a little bit, and thanks so much for your attention.
Thank you, Daniela. So succinct and provocative, maybe. So thank you very much. This has been recorded. We don't have time for questions, but this is a really nice introduction to a complicated subject. Thank you. Good to see you. And thank you all for joining, and we'll see you next time.
Thanks for your attention.
Thank you, Daniela.
Thank you, Sandra.